So we discussed the solution to this question in a very brief way, wherein we try to understand the requirement for centripetal force, condition of no slipping, and then slipping motion. And we also used loss of motion to solve the equation, right? Now what we do is let us try to understand this process in detail. So those who have watched it, those who wanted the short form of solution here, I have posted it here. Now others who are preparing for the first time, or those who want to understand the concept in really more detail, you can move on to the next section. So what do we have here? A disc, okay, with a flat small bottom beaker. So let us assume that there is some flat bottom beaker kept here, and it is from a distance r from the center. So this is from a distance r from the center. It's revolving. So this disc beaker is revolving around it like this. Okay. So yeah, about an axis passing through the center. So let's draw the axis also. So yeah, this is the axis, right? The coefficient of static friction between the bottom of the beaker and the surface of the disc is mu. Okay. The breaker will my bad, it is not breaker, it is it's beaker. Yeah, beaker will revolve with the disc if. So the straightforward answer to this is an object placed on top of the rotating top, which maybe rotating disc to be more precise. On the top of a rotating disc will revolve with it as long as the friction between the object and the top is static. Okay. See, I would actually suggest that you take notes along with me, right? Instead of focusing only for the answer, the numerical answer. Whenever necessary, please try to take note along with me while I dictate things, so things will become really clear to you. Okay. So see, that's what happened. If you listen and write simultaneously while I dictate the solution, you do it for one time, and then you'll understand that things. If you do it that way, things will last in your memory for a longer time actually. Okay, so let us now try to understand this process in detail, static friction, and how does it plays a role here. Okay, for that we'll first discuss about the requirement of a centripetal force. When an object is, this is what I'm trying to tell you, try to write this along with me. So when an object is placed on a rotating desk, it needs a force directed towards the center of the circular path to keep it moving in a circle. This force is called as the, well, it's not the central force, my bad. This is the centripetal force. All right. So when this object, or according to the question, when this beaker is placed on a rotating disc in this case, it needs a force directed towards the center, which means there will be a force acting like this towards the center always, right? Acting like this towards the center always. So wherever the body is, there will be a force acting on the body which is acting towards the center. Wherever the body is, there will be a force acting towards the center. Even in this position, it will act towards the center to keep this object moving in a circle. And this force is what we call as a centripetal force. So if you have to label this force is F centripetal. This force is F centripetal. This force is F centripetal. Okay. Now, one of the most common mistakes that we make is we somehow have a notion in the mind that centripetal force is some different force, is a different entity altogether. No, centripetal force in this case is not a third party force. It is in fact the force of friction between the bottom of the beaker and the surface of the disc. Okay. So give me a minute. Let me just try to explain you what that means further. So now let's discuss the source of centripetal force here. For an object on a rotating desk, the centripetal force, which acts like this, right? Which always act towards the center, is provided by the static friction between the object and the desk. In this case, it would be this would be F static between the between the bottom of the beaker, right, bottom of the beaker and the surface of the disc, right, and the surface of the disc. Static friction is what keeps the object from sliding off the desk, and enables static friction enables it to move in a circular path along the desk. Or in other words, simple words, it is a static friction which prevents the slipping of the object on the circular disc, right? What does it mean otherwise? It means that it is static friction, which prevents the slipping. Static friction prevents the slipping. Now what is slipping? So if slipping is prevented, slipping means velocity of beaker with respect to disc should not be equal to 0. So if that is prevented by static friction, it means that static friction tends to make the velocity of beaker the same as velocity of the disc. Okay, and when the velocity of beaker is the same as velocity of disc, what will happen? The beaker will move along the disc simultaneously. Okay, now let us understand the case of slipping. Now, as long as a central force is required to keep the object moving in a circular motion, which is okay, my bad. This is not central force. This is in fact as long as a centripetal force. So as long as a centripetal force is required to keep the object moving in a circle, this centripetal force, which is dependent on the mass, the speed of rotation, and the radius of the circle. F centimeter, which is m omega square by r, dependent on the mass, speed of rotation omega, and radius of the circle r. As long as this centripetal force does not exceed the maximum possible static friction. What does that mean? It means that as long as F centripetal does not exceed, is less than or equal to F static. Now, not just F static, the maximum value of F static. Now, what is the maximum value of F static? Exactly, the maximum value of F static is nothing but limiting friction, right? The maximum limit of friction, the maximum value of friction, or the maximum limit of static friction, which is what we call as the limiting friction, which is dependent on the coefficient of static friction mu(s) and the normal force N. The object will not slip. It will continue to move in a circle along with the desk. So I hope things are getting more clear to you now. Let's do it one more time. So as long as centripetal force, so how is centripetal force acting? Like this, right? Centripetal force is acting like this. Centripetal force is acting like this. As long as this F centripetal force is less than or equal to the limiting friction, what will happen? The object will not slip, and therefore velocity of disc will be equal to velocity of the beaker, as long as this condition is maintained. Okay, so we can say that the force required to keep the rotation, which force? The centripetal force required to keep the rotation does not exceed the maximum possible static friction. Now, what is the maximum possible static friction? Friction limiting. Therefore, F centripetal is less than or equal to friction limiting. Now, which body are we talking about? Are we talking about the desk or the beaker? Everything mentioned in this equation is respect to the beaker. So we have radius in which the beaker is rotating, mass of beaker, and normal reaction between the beaker and the disc. So this is where the free body diagram comes into picture. So if you consider this to be the free body diagram of the beaker, we have weight acting downwards, normal reaction acting upwards, and there is F centripetal always acting into the circle, right? So if sigma Fy is equal to 0 here, what do we have the value of normal reaction as? Normal reaction will be equal to N is equal to mg, right? Okay. Now, what is mb square omega square rb? It is F centripetal. So considering this equation, if you cancel out mb in both sides, why? Because normal reaction acting on the beaker due to the disk, right? Due to the disk is equal to mass of the beaker into g. Why? Because n is equal to mg. So n is mg here. mb by mb is 1. So what we have is mu s into g is equal to omega square rb. So radius of beaker should be less than or equal to mu s into g by omega square. Okay. So this is what happens for slipping condition. So this ensures no slipping. Okay. Now, see, if you want, you can just stop watching the content here. I would suggest, if you're happy with the answer, if you understood so far, things are okay. But I would actually suggest to spend a couple of minutes extra to understand what happens when there is slipping motion, which is okay. Well, give me a minute. Let us first read this part, and then we will try to visualize it. If the rotation speed increases or the radius increases, so it can be altered in both ways, in such a way that the required centripetal force is not central force, centripetal force exceeds the static friction, then the static friction can no longer hold the object in place, and therefore the object begins to slip. When the object begins to slip, what does it mean? It means that velocity of beaker will now no longer be equal to velocity of disk. Under which condition? When the centripetal force is greater than the limiting friction. At this point, friction becomes kinetic is the concept, right? And the object can no longer move along with rotating disk in a synchronous manner. In fact, it will slowly slip on the disk, and then it will fly away. It will fly off in a tangential manner. Okay. So I want you to visualize that part also. Give me a couple of minutes. I'll just try to bring the visualization as best as possible from my end. Now let me just try to make this visualization clear to you. This might be, see, there are limitations from my end while explaining this. I'll just try to make it as simple as possible. So we have one disk rotating in 3 different speeds, same disk. So omega d is 10 per second, 15 per second here, and 25 per second. So you can I think if you pay very close attention, you can see the variation on the speed of rotation. Okay. So let us say after this point, the limiting friction is less than the centripetal force. Okay. Now let us try to visualize what happens in these cases. So if you observe the first case, and if you give maximum constant, if you try to focus yourself, what you see is the speed of the disk here is actually equal to the speed of the beaker, which means there is no slipping. Why? Because velocity of disk is equal to velocity of beaker. Now let's see what happens in case 2. So you can very clearly observe that as I have increased the rotation speed of the disk, this beaker which was placed on top of it, it is still moving along with the disk in a synchronous manner, which means even in this condition, the velocity of beaker still is equal to velocity of disk, which means there is no slipping motion. Why? Because slipping motion means velocity should be equal to 0. Here the relative velocity is not equal to 0. Okay, sorry, not velocity, the relative velocity. Now, so far in this condition, what can we say? We can say that the F centripetal force is greater than is less than the limiting friction. Now what we need to understand is, as soon as limiting friction cannot withstand the F centripetal. Now, how will that happen? What is F centripetal? The F centripetal is given by m into omega square by r. So if I'm increasing omega by 2 times, the F centripetal becomes 4 times. No, that's what we're trying to understand here. So it is 15 and it is 25 here. So there's a significant increase in the omega, which means the speed at which now it is rotating is increased. Maybe I'll just try to make it more clear. Let us make this 30. Right? So the speed of rotation is increased 2 times, which means the centripetal force will now become 4 times. And the centripetal force now become 4 times. Let's see what will happen. So here, what will happen is, let's say if you place the disk here, it will try to move like this. But it will try to move like this. It won't happen, but at one point will just fly off. Okay. So, and that path will always be tangential. Why is it tangential? Because the velocity vector and the centripetal force here are perpendicular to each other, right? All right, so yeah, so that's something that I wanted to explain. So see, these kind of concepts become really important because the more time you spend in visualizing these concepts, the less time you'll have to spend in deriving the solution while in the exam hall. Because this visualization, the more and more, it's not about watching the solution. It's not about watching this visualization. It's about imagining this in your mind. The beaker, the disc, the contact between them, rotating, keeping a bird's eye view on this. So that's what important, because only then you'll be able to do the same in your exam hall. Okay, so if you practice the solutions directly, you won't be able to visualize well. That's why I say that in every question, visualization should be the first step, right? Okay, sorry that I took a bit long there. Let's move on to the next question.